Hi, this is Jared. For the presentation project today, I'm going to pick refraction, Snell's law as my first topic, and lens and mirror optics as my second topic. The first topic of the presentation is about refraction and Snell's law. Refraction refers to the directional change of light when it passes through different media, and it is a typical wave-like properties of light. As you can see, the beam of light is bent when transmitting from air into glass, and then bent again when it passes out of the glass. It may create distorted and interesting image, like in this case, a house may appear upside down. Refraction property of light can be described analytically by Snell's law. Snell's law can be written as sine theta 1 divided by sine theta 2 equals to n2 divided by n1, or n1 times sine theta 1 equals to n2 divided by sine theta 2. n1 and n2 are index of refraction with n equals to c divided by v, where c is the speed of light in the vacuum, and v is the apparent speed of light in the medium. Here is an example problem that applies Snell's law. With incident angle being 40 degrees, what is the refraction angle t? We can use Snell's law to solve a problem. n1 times sine theta 1 equals to n2 times sine theta 2. With theta 1 being 40, n1 equal to 1, and n2 equal to 1.32, then we can figure out that theta 2 equals to arc sine of n1 times sine theta 1 divided by n2, which equals to 29 degrees. This means the angle of refraction is 29 degrees. The second topic of my presentation today is about mirrors and lens, more on convex lens. I decided to talk only about convex lens due to the time limit. First, mirrors and lenses are optic devices that utilizes the reflection and refraction properties of light in our daily lives. My discussion today is on convex lens. In the convex lens, light rays refract at the lens plane. The curve of the lens are spherical. Refracted ray would converge, thus creating an image. Now, how to draw the light rays from a convex lens? There are three important properties to draw the light rays. The first property is that rays that are initially parallel to the optical axis passes through a far focal point. Rays that pass through the near focal point will end up parallel to the optical axis. Rays that pass through the center of the lens end up as straight lines. The intersection points of the light rays is the image location here. Now, to find the image distance from the lens, we need to apply the thin lens equation formula. The thin lens equation formula can be written as this. 1 divided by f equal to 1 divided by do plus 1 divided by di, where f is the distance from the focal point to the lens. Do is the distance of the object to the lens, and di is the distance from the image to the lens. Do and f are positive for convex lens. If the di is negative, then the image is virtual and on the left side of the lens. If the di is positive, the image is real and on the right side of the lens. The magnification of image is always defined as m equals to hi divided by ho, where ho is the object's height and hi is the image's height. It can be proved that m equals to minus di divided by do, where do is the distance of object to lens, and di is the distance of images to lens. If the magnitude of n is larger than 1, the image is magnified, thus enlarged. If the magnitude of n equals to 1, the image is the same size as the object. If the magnitude of n is less than 1, the image is reduced in size. If the sign of the n is negative, the image is inverted. Otherwise, the image is upright. Now let's look at an example of a convex lens equation problem. Given f equals to 30 centimeters, where is the image when object of height 40 centimeters is placed at DO equals to 60 centimeters? How tall is the image? We can solve this problem analytically or geometrically. To solve the problem analytically, we must use the thin lens equation, 1 divided by f equals to 1 divided by DO plus 1 divided by DI. We know that f equals to 30 centimeters, and we know that DO equals to 60 centimeters. We can manipulate the equation to get that 1 divided by DI equals to 1 divided by f minus 1 divided by DO. We find out that DI equals to 60 centimeters. Now we must find the magnification n. N equals to minus DI divided by DO, which equals to minus 1. Since n is defined as equal to HI divided by HO, HI equals to 40 centimeters. The image is 40 centimeters tall. Inverted, real image on the right side of the lens. We can also construct light rays through ray tracing with the 3 basic principles on how to draw the light ray. The ray that is initially parallel to the optical axis would end up passing through the far focal point. The second rule states that the ray that passes through the center of the lens will end up as a straight line. The third rule says that the ray that initially passes through the near focal point will end up parallel to the optical axis. The intersection of the rays is the image location. So the image is located here. Now let's talk about the relationship between Snell's law, refraction, and convex lenses. They are a pair of related topics. Both describe one of the wave properties of light, refraction. Convex lens is an application of Snell's law and refraction with specific materials and geometric shape to create images for use. Refraction in Snell's law may also be applied to other types of waves, such as sound and seismic waves. This is the end of the video. Please go on to see my post-check question in the next 2 slides. Thanks. Before finishing my presentation, let's talk about the post-check question. What happens when light rays travel from lower index of refraction medium into a higher index of refraction medium? What could happen when the incidence angle is very large? Take a pause and think about it for 5 seconds. Based on Snell's law, sine theta 1 divided by sine theta 2 equals to n2 divided by n1. We know that n1 is larger than n2, so sine theta 2 must be larger than sine theta 1. The refraction angle theta 2 is larger than the incidence angle theta 1. When the incidence angle is small, we see refraction with some weak reflection happening at the interface of the medium. When the incidence angle is larger than a certain angle, at the critical angle, the refracted rays would reach 90 degrees. Beyond that, total internal reflection occurs. Thank you for watching.